Okay, we are back, and this time we're going to be going over the cost function and how it applies to the algorithm that we're going to be using to find the best fit for our linear regression. So we're going to start off with the cost function again, where we have j of theta 0 and theta 1. It's equal to 1 over m summation I from 1 to m of, and inside here we're going to have our y hat I minus y I, and then we are going to square that value. Now this is what we got last time when we finished up for the cost function. This is our standard MSE, the mean squared error, but we're going to alter this just slightly. Our new function is going to be exactly the same. It's going to be j of theta 0 comma theta 1 is equal to 1 over 2m and times the summation. 1 to m, we have y hat I, our predicted value, minus y I, our actual data point, quantity squared. Okay, so this right here is our function with now a 2 in front of the m, and we have that 2 there for reasons that you'll see in the next video. It's for the math, the calculus, makes it a little bit easier to have that 2 there. Okay, so now this 2 won't affect things, because you can imagine if I had something like my summation was equal to 50 for one cost function, and the summation was equal to 60 for another summation. If I multiply these by 1 over m, maybe m is 10, I get that this one has a cost of 5 and this one has a cost of 6. Now, if I change that to a 2m, so 20, now instead of the 5, I'm going to wind up with 2.5, and this instead of a 6 will wind up 3. But the relationship is still the same. This function is still the minimum between the two. It doesn't matter that I scale it by a factor of 1/2 or not, it still preserves the same relationship. So we're going to keep the 2 there for now, and we will be using it for the calculus portion of this algorithm next video. But for now, we're just going to assume that that 2 is there, and we're going to run with that. So this function right here is my new cost function. Alrighty, 1 over 2m times the summation y hat I minus yi quantity squared. Okay, so now that I have that, let's move to a way to interpret this y hat. Alrighty, so let me clear the space. We're going to start off with saying that my y hat I, well, that is the predicted value of y from the equation, right? Well, that predicted value of y, that is what I will get when I feed an x in. I'll get a y out to the equation of the line, and what we said is that this was equal to theta 0, the y-intercept, plus theta 1 xi. Okay, that was my hypothesis function, and it lets me put an x in and get a y value out, or predicted y value. Okay, now I'm going to work in this example with the simplest setup I can imagine, where I have 3 locations are going to be at 1, 1, 2, 2, and 3, 3. Okay, and you can imagine, assuming I drew this correctly, there is a line that best fits that, and that line is going to be y is equal to x, or to be very explicit, there is a 1, if I can draw that, right in front of the x, so that's a 1x, where the slope is 1. So for this line right here, I'm going to have my b, or my theta 0, equal to 0, because it's passing through the origin, assuming I can draw. This is 0, 0, the origin. And my m, or my theta 1, that is equal to 1. This is the line I know will give me the absolute best fit through these 3 simple data points. Okay? But we are going to assume that we don't know that, and we're going to let an algorithm figure it out for us. Okay, we have cleared the screen, and we are now going to talk about one final simplification. Our first simplification is that we have the 3 points located at 1, 1, 2, 2, and 2, 2, and 3, 3. The second simplification that we're going to do is, instead of having y is equal to theta 0 plus theta 1x, is we're going to make theta sub 0 equal to 0. Now if we do that, our predicted y is simply going to be theta 1 times xi. That is our simplified version of how to figure out what the predicted y value is. So now, with that in mind, we're going to have our cost function is now going to be a function of just theta 1, and it's going to equal 1 over 2m summation. And for our predicted value, we're going to have, instead of y hat I, it's going to be theta 1 times x I. That value minus the actual y value, yi, and I need to square that and bracket it. Okay, so this is going to be our new cost function that we're going to use for evaluating all the different values of theta 1. Now, the next thing we're going to do is going to seem a little strange. I'm going to clear the screen again. We are going to graph. This is going to be very odd initially. I'm going to have theta 1 on the x-axis and j of theta 1 on the y-axis. Okay? I'm going to have values, let's say that right here, 0.5, right here, 1, 1.5, and 2. Okay? Now, what I want to do is evaluate the cost function, where the cost function is j of theta 1 is equal to 1 over 2m summation I from 1 to m of, I've got my new expression for my y hat, which is theta 1 xi, minus the actual y value, yi, quantity squared. Alright, so that is my new cost function, and I'm now going to evaluate for several different theta 1s. Okay, and I know that my points on the original function were at 1, 1, I'll even list them out right here, 1, 1, 2, 2, and 3, 3. Okay, let's start with, I'm going to change colors. I'm going to go blue for the very first one. let's look at j of 0. Theta 1 equals 0. So we're going to have a slope of 0. Okay? Slope of 0 would give us, well, the cost function. I have 3 points, so it's going to be 1 over 2 times 3. And then I'm going to have that multiplied by the summation of the 3 points being evaluated, the difference between the predicted and the actual. So here we go. I'm going to start off with theta 1, 0, times the x value of the very first point, that's 1, minus, and I'm going to have the y value of the first point, 1, so that is going to be squared, and make a big bracket right there, plus, next point, I'll have 0 times the x value for the second point, which is 2, minus the y value of the second point, that's going to be squared, and then finally, I'll have the third point. My theta 1 value is 0 times the x value 3 minus the y value 3, quantity squared, and bracket. Okay? This is going to give me 1 over 6 times, well, this expression is 0 minus 1 squared. That's going to be a 1 plus 0 minus 2, which would be negative 2 squared, for 4. And then over here, it's going to be 0 minus 3, quantity squared, which is negative 3 squared, or 9. Okay? So I'm going to wind up with 14 over 6, which is approximately 2.3. Okay? So for theta 1 equal to 0, which is the value right here, I am going to place a point, my cost function. Let me actually write the actual cost on here. So I'll also have a value of maybe 1 here and 2 here. Put the 0 down right there. And now let me place my dot. I've got 0, 2.3. So somewhere around right there. Okay? Now, let's run a different one. And I will magically erase all of this. I hope anyways that I can knock that out. Okay, now let's take a different slope. Let's do j evaluated at theta 1 is equal to 0.5. Okay, that will equal 1 over 6, big bracket, little bracket. We'll have my slope, which is this theta 1 right here, which is 0.5, times the x value for the first point, 1, and then that will subtract the y value for the first point, 1, square that, then add in the second point, so 0.5 times 2 minus 2, and then finally for the third point we'll have 0.5 times 3 minus 3, bracket, square, and bracket. Okay, so let's evaluate this. This is going to be 1 over 6 times 1, so 0.5 times 1 is 0.5, minus 1 is negative 0.5 squared, which is going to be 0.25, plus, this is going to be 0.5 times 2, which is 1, minus 2, which is negative 1 squared, positive 1, plus, this gives me a difference of 0.5 times 3, which is 1.5, minus 3, which is negative 1.5 squared, which is 2.25. Okay? That is 1 over 6 times, let's see, that's going to be 0.25, and 2.25 is 2.5, plus 1 is 3.5. So 3.5. And this is approximately 0.58. Okay? So for theta 1 equals 0.5, I'm going to put a point at 0.58 somewhere right in there, and I'm going to add this to the list up here. Theta 1 is equal to 0.5. Okay? Now I'm going to repeat the process by clearing the screen and going for a different theta 1 value. Okay, now let's look at when theta 1, our slope is equal to 1. So I can get it to work. J of theta 1 is equal to 1. That's going to equal 1 over 6 times big bracket, little bracket. I'm going to have my slope, 1, times the x value of the first point, 1, minus the y value, 1, quantity squared, plus I'll have my slope, 1, times the x value of the second point, 2, minus the y value of the second point, 2, quantity squared, and then plus I'll have my slope, 1, times the x value of the third point, 3, minus the y value of third point, 3, quantity squared, and then all of that bracketed in. So my cost function is going to be 1 over 6 times, well, 1 minus 1 is 0, squared is 0, 0 plus 0 plus 0. All of these are going to wind up being 0, which is what we expected, because we saw already that a slope of 1 would pass exactly through all of the data points. So this winds up having a cost of 0. So if I place that on the graph, a slope of 1 has a cost of 0. So this is that data point right there. And I will add it to the list, which I forgot to do the green. That's fine. Theta 1 is equal to 1 is in the red. Okay? Now, I'm going to erase this and continue on. Okay, now let's look at a couple more slopes. It turns out, due to symmetry of the slopes, when theta 1 is equal to 1.5, this is the exact same cost associated when theta 1 is equal to 0.5. Okay? And by that same logic, if I have my theta 1 is equal to 2, that is exactly the same cost associated with theta 1 equal to 0. I'm going to place those 2 points up on the graph. Let's see, do the theta 1 is equal to 1.5 first, at that point, and then I'll do the theta 1 is equal to 0 point here. Now I'm going to connect them all with a nice smooth curve, or I will attempt to do so. So if I connect all these dots with a smooth curve, I get something that looks like that. And that is a parabola. And this parabola, I give it a theta 1, a slope, and it tells me the cost associated with that slope. Okay? Now that we have this graph developed, it's going to be time to actually go through the algorithm and see how the linear regression algorithm chooses the best fit every single time, no matter what type of slope we start off with as a guess. So let's try that. Okay, so the algorithm that we're going to be using is very famous in machine learning. It's called gradient descent. And it is as follows. My new theta value is equal to the old theta value minus alpha times the partial derivative of the cost function with respect to theta 1. Okay, that is the gradient descent algorithm. What I haven't defined yet is this alpha. So this alpha is approximately, the way you can think about it, it is the learning rate. And it decides how fast the algorithm attempts to find the minimum solution. If you have an alpha that is too large, it will not zero in on the solution. It will wind up diverging, and the theta value will go up to infinity. If the alpha is too small, it will take a long, long time for it to find the minimum. So you need something that is somewhere between divergence and taking an infinite amount of time. Now, experience, and this is only through experience, is that a good starting value, maybe something like 0.1. This did not fall out of the sky. This is from running algorithms many, many times and observing that a learning rate of 0.1 is usually a decent place to start. It's not too small of a step size, but at the same time, it's large enough to where it will converge in a decent amount of time without diverging. Hope I said that correctly. So this alpha we're going to say is 0.1, and now we're going to run gradient descent. So here we go. I want to make my initial guess. For theta 1. Oh, let's let it equal theta 1 equals 0. Okay? So with that in mind, let me clean this up just a little bit. Theta 1 is going to equal to 0. Alrighty. So erase this. I've talked about it. And I can even erase most of this and just rewrite it as alpha is equal to 0.1. Okay. So now my new theta is going to be my old theta, which I said I'm going to start with a guess of 0, minus 0.1 for my alpha times the slope of my cost function with respect to theta 1. Where could I find the slope of the cost function with respect to theta 1? I wonder where. That's the reason that I made this graph in the first place with this parabola, because now we don't actually have to do the calculus behind it. We can actually just look at the graph and see that the slope at theta 1 is equal to 0 for right here. Maybe that's a -2 slope. That works for me. -2. Okay? That's going to equal, when I have -0.1 times -2, I'm going to get a new theta value of positive 0.2. Okay? So that is going to be what my old theta value is. So now I run through the algorithm again. I have theta new is going to equal the theta old, which in this case we just found was going to be 0.2 minus 0.1, and then that's going to be multiplied by the slope at around 0.2. Theta 1 is 0.2, maybe it's around there. So come up here, now look at this slope right here. Maybe it's a little bit less. It should be if I draw my parabola correctly. Maybe it's negative 1.6, just as a guess. Okay, so that's going to be 0.2 plus 0.16, which is going to give me a new theta value guess of 0.36. Okay, now let's run through the algorithm again. Theta new is going to equal, my old theta, 0.36 minus 0.1 times the slope at the value 0.36. Maybe that's somewhere around here. Actually, looking at that, it's probably closer to here. If I look at that slope right there, it should be a little bit less steep than the ones that came before. So maybe that's negative 1.4. That would give me 0.36 plus 0.14, which would give me a new theta value of 0.5 right here. Okay? So now, let me erase this. Take all this out, and then I'll work on the other. Okay. Erase all of this. Nice. Okay. So, my theta values that I started off with. Well, they started off with a value of 0, and after they iterated, it became 0.2, 0.36, and 0.5, right? What's happening to my theta 1 guess? Well, the distance between my first two guesses is 0.2. Between the next guess, it's a value of 0.16, and then the next guess, that amount is 0.14. So what we can see is that the amount that the theta 1 value, the slope guess, is changing is slowly decreasing. Started with 0.2, next guess was 0.16, next guess was 0.14. What's going to happen as my guesses get closer and closer to right there at the slope, theta 1 equals 1? Well, what's going to happen is, since my old theta, my new theta is equal to the old theta minus alpha times the slope, as I approach this minimum, my slope is going to be going down. That value is going to be decreasing. That's supposed to be an arrow. It's going to be heading down. And as I get really close to this minimum, and then finally almost touch the minimum, you can say that the slope of this is going to be approaching 0. And when the slope is 0, when I have a 0 right here, this whole term is going to be 0. So I'm going to wind up with the condition theta new equals theta old. My new guess is exactly the same as my old guess, and when that happens, we have found the minimum. That theta value is the absolute best fit for the line through the 3 points. And we did the whole thing with just a graph of the cost function so that we could look at the slopes. Okay, so I've threw things off, but I wanted to make one quick point because I haven't talked about it yet. And that is, well, we started over here to the left of the minimum with our initial guess for the slope. But what if we started over here on the right? What would happen? So let's take an initial guess at theta 1 value of 2. So let's say theta 1 is equal to 2. So we have our theta new is going to equal the theta old, 2, minus, I've got my alpha, 0.1, and now I have the slope, and we'll say that this is symmetrical so that the slope on this side is the same as the slope on this side, except now it's positive 2. Okay? When I do that, I'm going to wind up with 2 minus 0.2, which is 1.8. So my next guess moves over. So somewhere around here, 1.8, right there. I can draw a decimal. So the next iteration would be theta nu equals, well, the old theta, 1.8 minus 0.1. Now the slope is not going to be quite as steep. Maybe it's 1.6, which is going to be 1.8 minus 0.16, which is going to give me a value of 1.64, which moves me over to here. So I started out at a guess of 2, I moved to 1.8, and then I went to 1.64, and you can imagine I'm going to continue until I reach the minimum from this side. And again, when my theta 1 old matches my theta 1 new, I'm going to wind up with a 0 for the slope, which is where the minimum is. So when theta 1 is equal to 1, again, I will have my minimum. So it doesn't matter where I start. I can start over on the right side. I can start on the left side. It doesn't matter how far out I go. This algorithm will always approach and slow down and finally reach the minimum, the value right there at the bottom of the parabola where my theta, my slope of my cost function is 0. And then the algorithm will stop. So that is why gradient descent works. It intelligently adjusts towards the minimum. That is one of the key points of machine learning and why it works, is that when it makes a guess and then it runs the algorithm to update that guess, my gradient descent, oops, do it like that, algorithm is always headed towards the min. It is not randomly guessing and adjusting. It is heading in a stepwise manner to the minimum. This is why it will converge to the min every single time without fail. And this is why this algorithm, why the machine learning has an advantage over some of the previous algorithms, which might adjust by a random step size. Since I would say 80% of the machine learning algorithms use some version of the cost function paired with a gradient descent. This is one of the most important algorithms concepts that exists in machine learning. So if you have the cost function, hypothesis function, and the gradient descent, you have 3 of the key components that are used in just about, I'd say about approximately 80% of the machine learning algorithms. So this is one of the gateways to learning about machine learning, is that almost all of the algorithms share the common components of the cost, hypothesis, and gradient descent. Okay, so last thing I want to talk about is the alpha. We said that our alpha was equal to 0.1 and that was just a good guess that would allow convergence in a timely manner. If my alpha had been something very large, like, oh, let's make the alpha 5, then my algorithm for the gradient descent would be my theta nu is equal to my theta old, which, you know what, let me just go ahead and place a guess of 0 in right there. So we'll say 0 minus the alpha, which is now 5, times the slope, which would be -2 at that location. So my new theta is going to be located at 10, which is way over here somewhere and way up. So I bounced, when I did it like that, I wound up bouncing over the parabola min. If your alpha is large enough, that's what will happen. You'll wind up bouncing out of the parabola, and you'll wind up diverging and going towards infinity. So this is eventually going to head to infinity as a guess for my theta. Conversely, if I make my alpha super small, let's say alpha is equal to 0.000001. Well, you can imagine my theta new is equal to my theta old 0 minus, well, 0.000001 times the negative 2. So now my theta new value is going to have a value of 0.000002. This is going to take a long time to finally reach the minimum. We're guaranteed that we're not going to diverge and go to infinity with such a small step size, such a small learning rate, but the algorithm will take many iterations. This one would probably be in the millions of iterations to finally hit the min. Whereas a step size, when I'm talking about a theta, an alpha rather, of 0.1, most of the times this is going to converge in about 20 iterations tops, depending on where you start and what the points look like. And so this is pretty much the conclusion of the lecture. The main takeaways from all this are the gradient descent algorithm, how it works. It nudges in the direction of the derivative of the cost function, which this time we did graphically with the slopes. But next time we're actually going to use calculus to find those derivatives. And that while we're using the gradient descent, our step size, alpha, is critical in determining on how long it takes to converge, if it converges, which it won't in the case of a large alpha. And that's about it for this lecture. The next time we'll be going over the actual computer code that will define this algorithm and run it in Python and see what we get. So until then, take care, and I will see you later.